对于同样一个电路，好，那对于同样一个电路呢，如果我的 input frequency 就是我给它一个 signal， 然后这个 signal 的 input frequency 改变的时候，不同的频率，事实上呢，这个电路给的反应会不一样。好，比如说呢，比较低频的时候，这个电路是放大的，但是呢，再高频一点呢，它还放大，但是幅度变小，放大倍数变小，好，甚至到最后它已经变成缩小了哈。所以虽然电路是相同的，但是呢，在不同频率的信号之下，它的表现不一样。好，那所以呢，基本上可以画出一个类似像这样的东西哈，就是 gain 的 roll off。在比较低频的时候呢，可能还有一定高度的 gain 好，但是到了某个频率之后，它的 gain 就越来越小。那我们把这一个地方叫做 bandwidth 好，也就是这个电路的频宽。为什么你的这个 voltage gain 会往下掉呢？哈，那我们就看到说，好，那因为在这个电路从 input 到 output 的 signal path， 好，这个信号的这个流的过程，那条路径上面，其实呢都会有非常多的寄生电容。好，那每一个电容呢，只要它是一个寄生电容，它把这个 node 连到 ground。那只要我操作的频率够高，它就会变成一个很小的电阻 ，OK， 那就有点像把它 short 到 ground 哈。所以不管你的电路怎么设计，只要频率够高，这些 signal path 上面的 node 的电压就会被拉到0了，所以它当然会掉下去 ，OK。那我们拿了 common source amplifier 做了一个例子，好，比如说我在 output 的地方如果有这个的话，我的 output 的 signal事实上就会有一个 S term 啊，就是因为这个电容，所以就多了一个跟频率相关的 term 这样子哈。那昨天我们也稍微讲了一下，所以我们在看 voltage gain 的时候呢，如果把频率的效应的这个事情带进来的话呢，我们所看的 voltage gain 也就是 V out 除上 V in， 就会变成在什么地方？信号与系统的时候学的 transfer function 这样子，好 ，transfer function 事实上就是看一个系统输入和输出之间的关系。好，那这个 transfer function 可以被写成这个样子。好，那它整个 transfer function 的绝对值，也就是它的 magnitude， 就决定了呢我 input 和 output 之间振幅的大小的变化。好，那另外一个呢就是个 transfer function 的 phase。这个 phase 呢，就决定了我的 input 到 output 会不会 delay， 好，会延迟多久这样子。好，那所以这个 transfer function 对于我知道这整个系统怎么工作，其实是非常重要的。好，那再来呢，我们看了一下这个例子，好，那这个例子呢，事实上呢，就是在讲到说，好，我们就用刚才的这个common source amplifier， 然后呢，看它的 transfer function。那我们在它的 transfer function 里面找到一个很特别的频率，好，那这个很特别的频率呢，以这个地方来看呢，就是让这个项等于1的时候，好，也就是 S 等于RDCL 分之1的时候，好，那因为 S 是 J omega， 所以它是虚部的，那所以这个东西omega 等于这个的时候呢，你的实部是1，虚部是1，它的 magnitude 就是根号2，好，根号2。那我把所有的这些voltage gain 都用这个 decibel 取为它的单位的时候呢，我就会把所有的 voltage gain 昨天讲过，取 log 再乘上20，好，那根号2取 log 再乘上20就变成就变成3这样子，好，所以简单来说。在这个 frequency 的时候，你的 voltage gain 会变成原本的这个 voltage gain， 好，减掉3个 dB， 减掉3个 dB， 好，我们把它叫做3 dB 的 frequency。这个3 dB 的 frequency 呢，事实上就是原本的 voltage gain 的70%，好，因为根号2就是1.414，反过来就是0.707，好，所以它是原本 voltage gain 的70%。简单来说，就是我们把这个3 dB 的 frequency 呢，定在你的 voltage gain、你的放大效果，还有原本你设计的70%，好，切在那个地方这样子。好，那最后呢，我们昨天其实到最后是到这个地方哈，我们就稍微看了一下这个 我们的 transfer function 好跟这个所谓的 step response 有什么关系 ？bandwidth 跟 step response 之间的关系哈。那你有看到这个 bandwidth 的那个 cutoff frequency 呢？事实上是 RC 分之一 ，OK。然后呢，你的电路学如果还有一点印象，也没有完全还给老师的话呢，这个电路学如果有个 step function， 它上去的这个所谓的 time constant 也是 RC 好。所以简单来讲呢，就是RC 越大，它就需要越久才能够到达稳态这样子。好，那 RC 越大呢，这个cutoff frequency 也是 bandwidth 是越小的。好，所以从这个例子，大家可以有个概念记得的，就是说，好，我的 bandwidth 越小，我的电路的速度就越慢。OK， 我的 bandwidth 越大，我的电路的速度就越快，这样子，好不好？这是 frequency domain， 这是 time domain。好 ，frequency domain 你有一个比较大的 bandwidth， 你可以有比较高频的频率的成分的时候呢，你的电路的反应速度是比较快的。好，我们昨天就到这边。So today we will move on. This is the frequency response plot, right? And if you want to plot every point, actually this is very tedious. There are a lot of work for you to do if you want to just plot the whole thing. So you can, of course, you can use H-Spice and you can do some simulation. But when you design the circuit, you just want to quickly have some estimation about how your frequency response will look like. How do you do that? Okay, a very smart person called Bode proposed this. He said that we can use these Bode's rules to develop the frequency response plot easily and quickly. 好，简单来讲，这个 Bode plot 呢，就是Bode 这个人呢，他想了一个办法。这个办法就是说，如果你写得出 transfer function， 你就可以很快的画出一个 Bode's plot。这个 Bode's plot 呢，长得跟你的 frequency response 呢很像，是一个近似啊。Okay, so if you take this transfer function and if you take it into the unit of decibel, you know that you have to take the transfer function and log and times 20, right? So 20 log h of s will equal to what? Will equal to 20 log A0 plus 20 log, right? And plus, and minus 20 log 1 plus S omega P1, right? So you can see one of the reasons we want to use the unit as decibel is that if we take the log, actually we can separate each term easily, right? We can separate each term. A0, the 0 number 1, 0 number 2, pole number 1, pole number 2. So we can separate them, okay? And what about this? This is DC gain, right? Or low frequency gain. So this is a constant. For example, it's maybe minus GMRD, okay? So this is a constant. A constant, take a log, is a number. And times 20 is another number. So this thing is just look like this. So if you draw this one, omega, and this h of s, so this is the 20 log something is just a constant. It's just a flat line like this, right? So this one is very easy. What about this one? This term, okay? So talking about this term, 20 times log 1 plus s over omega z1, okay? Well, it's difficult to actually plot every point, but we can use two lines to approximate this one. Okay. First, when S is equal to 0, or when S is very small. When S is very small, or S equal to 0, you see this is S, right? Let's say this one is f of S, okay? So when S is equal to 0, this is 0, right? This is 0, this term is 0, only 1 is left here. And what is log 1? Log 1 is 0, right? So 20 log 1 is 0. So when S is equal to 0, actually f of S is equal to 0. Okay, easy. And when S is very large, okay, if S is very large, we see, what about this? What is this? F of S in the absolute value will be equal to 20 log square root 1 plus omega over omega z square, right? Because S is equal to j omega, which is the complex part. Okay, so if we want to take the magnitude, it's 1 square plus omega over omega z square. So when omega is very large, actually this will be approximate to 20 log omega over omega square and take the square root, right? This term can be omitted. Okay, so only this term is left. And this is equal to 20 log omega over omega z. Is it okay? All right. So basically, what does that tell you? That tells you that when the frequency is large, you can see the relationship between omega and the magnitude of the transfer function is when omega becomes like 10 times, let's do this, okay. So from here, if omega is equal to omega z, okay, and we substitute this into here, what are you going to get? Your f of s will be equal to 20 log omega z over omega z, right? Omega z over omega z is 1, so log 1 is 0, so this is still 0. What about if omega is equal to 10 times of omega z? If omega is 10 times of omega z, your f of s, absolute value of f of s is 20 log 10 times omega z, right? This is 10. Log 10 is 1, so this is 20. Right? So when omega is 100 times omega z, f of s is 40. Right? Okay. So what does that tell you? Actually, if you plot this, this is omega, this is f of s. From here, and here, and here, you are going to see this plot can be approximated by 2 lines. Here is omega z. Before, when omega is smaller than omega z, actually, this is 0, right? When s is very small, it's 0. Oh, okay, I have to say that this is log scale, and this is also log scale. Okay, both the x-axis and the y-axis are log scale. Okay, so this is actually not 0. This is when omega equal to 1. You understand this? Okay, because this is log scale, so here is omega equal to 1. It's not omega equal to 0. Okay, so this is omega equal to 0.1, 0.01, 0.001. Okay, so before, when omega is smaller than omega z, actually the magnitude of the transfer function is 0. When omega is larger than omega z, every 10 times, say this is 10 times omega z, this is 100 times omega z, 10 times omega z is 20 dB. Oh, okay, sorry, I was wrong. The y-axis is not log scale, it's the linear scale. Sorry, I was wrong. This is called semi-log. So this is linear scale. Okay? The y-axis is linear scale. The x-axis is log scale. So this is called semi-log. So this is like this. Something like this. Okay? So what's the slope? This slope is actually plus 20 dB per decade. What does it mean by decade? Every 10 times. 好，就是频率每多10倍，它就会上升20 dB 这样子。好，怎么来的？好，可能从来没人告诉你怎么来的，就是这样导出来的这样子。OK， 所以 for 这个 term， 基本上呢，每一个这个 term 你都可以画一条这个线。OK， so this is for a zero. And what about for a pole? For this pole, actually it's minus, right? So you are going to see something like this to the other direction. Okay, if it is a pole, well, let's draw another one. So if it is a pole, it's going to be like this. Okay, so it's minus dB per decade. It's for omega p, which is the pole. So for a constant value, you are going to get a constant line here. If it is a 0, you are going to get something like this. If it's a pole, you are going to get something like this. Okay, and to construct the whole transfer function, you just add each term all together on the same plot. And then you can construct the Bode's plot. Okay? How? Okay. So this is what this means. As omega passes each pole frequency, the slope of the magnitude of the transfer function decreases by 20 dB per decade. And vice versa for the zeros, it increases by 20 dB per decade. Let's use one example. As example 11.7. So let's come back to the common source amplifier example. Let's use the Bode plot, okay, to construct the frequency response. Remember, the transfer function of the common source amplifier is this. It's minus GM times RD in parallel with 1 over SC, right? And remember, we write down this one. And if we write down this one, actually we can rewrite this. Okay, so for this transfer function, h of s is equal to minus GMRD 1 plus RDCL times S, right? So actually we can write it as minus GMRD 1 plus S over omega P1, and omega P1 is equal to RD CL in the denominator, right? So this is what we are going to get. And let's construct. So basically, there will be two things. Well, this is omega. This is the transfer function in magnitude. Here, the first thing is the GMRD. So basically, we will have one line like this. This is called 20 log GMRD. Okay? Another one is this one. This one will be something like this, right? This is minus 20 dB per decade at omega P1. So basically, we can take the log and times 20, and we can construct the whole transfer function by taking this into two separated parts. One is here, one is here. So the total transfer function will be these two adding together. So the total transfer function should be the yellow one. Okay, so the total transfer function should be something like this. Okay, so you will see the total transfer function will be something like this. Okay, because we add these two together, resulting in the yellow line. And the yellow line is what we got from the body plot. Okay? This says GMRD, actually, you should take log and times 20. Okay? And if you still remember, it looked very similar to the frequency response we plotted yesterday. Okay, so this actually you can get from measurement or simulation. Okay, this you can get from the Bode plot. What is the difference? Remember, at omega P1, at this frequency, actually the magnitude of the transfer function should be 3 dB lower than the low frequency gain, right? So basically, there will be some error right here. This is the accurate plot. This is an approximated plot. Okay. 所以呢，我想讲的是 Bode's plot 是一个近似的画法。好，我们用两条线 We use two lines. One is this line, and another one is this line. We use these two lines to approximate a line, which is the actual line, is like this. 真正应该是这个粉红色的线，但是我们用了两条黄色的渐近线去近似它。最大的差别就在这里，这里有3 dB 的 difference。OK， 粉红色的这一条是真正的，黄色的这两条是近似它的。OK， so using Bode's rules, actually we can do very good approximation. Okay, but you have to keep in mind, actually, at the pole frequency right here, the actual magnitude is actually 3 dB less than the low frequency magnitude. Okay, 所以它会有一点近似，然后它会有一点误差，误差只有差一点点这样子。Okay, so this is Bode's plot. After the Bode's plot, actually we have already introduced how you construct the frequency response. If you know the if you know the zeros, if you know the poles, actually you can construct the whole frequency response easily. Okay, and here actually you can get some feeling that, oh, if I have a resistor and if I have a capacitor, this resistor and this capacitor altogether may form a pole. Okay, so one idea is that if you have a node, and if you have, if at this node you have a capacitor connecting to ground, somehow this node may be short to ground when the frequency goes very high. Okay, so this you will expect there will be a pole right here. 好，就是只要是一个 circuit node， 然后这个 circuit node 呢有一个电容接地，你就可以想象这个 circuit node 会有一个 pole， 因为 eventually 只要频率够高，这里就会被拉到地这样子。OK， 那这个 pole 在哪里呢？就是 RC 分之一。你只要看到一个 node 有一个 capacitor， 你就可以有一个想法说可能会有个 RC 分之一。Okay, so if we generalize this idea, okay, generalize from the common source stage, if node J in the signal path is hit at a small signal resistance of Rj to ground and a capacitance of Cj to ground, then we will have a pole Rj Cj 1 over Rj Cj. Okay, 就是你在 signal 的 path， 所谓的 signal path，what do we mean by signal path? The path from the input to output. That's the signal path. Okay. So if we have a node in the signal path, and at this node you send some capacitance connecting to ground, and you also send some resistance connecting to ground, then you will have a pole which value is 1 over RC. Okay, let's give you one example quickly. 11.8 determines the poles of the circuit. Okay. Well, you see here we have a capacitor going to ground, right? And the small signal resistance you see is from here, infinite in parallel with RS. So you have RS 1 over RS Cin right here. We say that we have a pole here. And at the output, we have a CL to ground. Okay? So what about the resistance? The resistance is RD in parallel with RO. Okay, if we want to make it simpler, we neglect RO, then we will have another pole RDCL in the denominator is 1 over RDCL. Okay, so 2 nodes, 2 capacitance, 2 poles. Okay, so the transfer function might be this. We will have 1 pole here. We will have another pole here. We should have a line here. 我们应该这里要画一条那个除的哈，没有画好，你自己把它画上去。OK， 每一年我都请大家自己画上去，因为我懒得改了。OK， so we can quickly write down the transfer function like this. Okay, so from this example, actually you can see signal path from input go to the output, right? So along the signal path, actually you have 2 nodes. One node is right here. You have 1 pole, and another node is here. You have another pole. So in this circuit, you are going to see 2 poles. So this is a 2-pole system. And what about 11.9 example? Again, this is a common gate amplifier. The input signal goes into here and come to here, right? So along with this signal path, actually you have 2 nodes. One node have Cin to ground. What's about the resistance is Rs in parallel with 1 over Gm, right? So you will have 1 pole Cin times Rs in parallel with 1 over Gm, and this will be in the denominator. And what about this? Is 1 over RDCL, right? So you will have 2 poles. Okay, so this is just quickly tell you that if you see some nodes from the input to the output, and each node you have a parasitic capacitance connecting to ground. You are going to get one pole at that node, okay? But I can tell you right now, this is just an approximation. Actually, this is not very accurate, okay? The number of poles is accurate. The order of magnitude will be approximately good, but actually the accurate number is not good, okay? 我们刚才讲这一页呢，我很快用这个中文讲一次。从 input 到 output 的整个 signal path， 好，你看到几个 node， 每个 node 都会有一个寄生电容接地的。你只要看到寄生电容接地，就表示那边一定只要 frequency 够高，它就会被拉到地，对不对？所以你就会有一个 pole， 这个 pole 就是 RC 分之一 ，OK？ 所以呢，比如说左边和右边呢这两个例子，你都可以看到两个 node， 这两个 node 都有电容接地，对不对？所以呢，你就可以看到一个 RC 分之一的 node， 还有另外一个 RC 分之一的 node。好，然后你就可以马上把它写出来。这是看起来是 OK 的，其实是87% OK 吧？嘿，好，它就是没有那么 OK 的原因是这样：如果这里有两个 node， 它会有两个 pole， 这件事是对的。然后呢，你在算这个 pole 的时候呢，它的 order 也是大概是会对的。举例来讲，你算这个 pole 呢，在100 MHz， 那可能你就会得到一个数百 MHz 的 pole， 反正那个数量级是对的这样子，但是那个准确的值不会是对的。好，我们之后就会看到了，你的准确值是不对的，但是数量级会是对的这样子。好，这里留一个伏笔，因为后面才会看到这样子。Anyway, if you look at this, you will know that this will be the bottleneck of your speed, right? Because remember, we discussed one example in 11.6. Do you remember the relation between bandwidth and step response, right? If your bandwidth is smaller, actually your step response will be slower. Okay, so that actually will be your bottleneck of the speed of your circuit. Okay, so anyway, this is still easy because you just need to identify the capacitance if you have a capacitance between a node and ground. But what happens? What happens when you have a capacitor, but it's a floating capacitor? Okay, for example, if you have this capacitor and this capacitor connect this node, and both nodes are not ground, so we say that this capacitor is a floating capacitor. We just learned that if we have a grounded capacitor means that one terminal of the capacitor is connected to ground. But this is not a grounded capacitor, this is a floating capacitor, which means that both terminals of the capacitor are not connected to ground. Okay, they are connected to somewhere. So how does this affect your frequency response? Well, we can use a theorem called Miller theorem. And we can use the Miller theorem to simplify this circuit. Okay? To tell you, Miller theorem is to make a floating component into two grounded components. Okay? 我们如果有一个 floating 的电容怎么办呢？我们可以 apply 这个 Miller theorem 米勒定理这样子。这个米勒定理呢是一个数学定理，它可以把一个 floating 的元件变成两个等效的接地元件这样子。那接地的 capacitance 你就知道怎么办了这样子。好 ，so we can use Miller theorem to calculate to make this floating capacitor into two equivalent grounded capacitance. And why does it call Miller theorem? 为什么它叫做米勒定理呢？ Because it is invented by someone whose last name is Miller. 好，就是它是被一个姓米勒的人提出来的，所以它就叫做 Miller theorem 这样子。好 ，What is Miller theorem? Miller theorem is a method that can transform a floating capacitor to two grounded capacitors. Well, it doesn't, it is not limited to capacitors. Actually, it can be used for any impedances. Okay, so let's look at this. This is a general circuit including a floating impedance. Okay, it is not necessarily a capacitor. It could be resistor or inductor. If there's a floating impedance connecting between two nodes, one is node number 1 and the other one is node number 2. Okay, so at node number 1 we have a voltage, no voltage V1, and node number 2 we have a no voltage V2. What if we want to make this thing equivalent to this? Okay, we want this two to be equivalent. Okay, from one floating impedance to two grounded impedances. To make them all equivalent, we just need to fulfill KVL and KCL. If you can fulfill KVL and KCL, then this node, all the circuit elements right here, is not going to know, well, this impedance is floating or is grounded. Okay, 这里有一点需要讲一下，怎么样让这个等效于这个呢？你只要让这边所有的电路的元件都觉得这样和这样是一样的，好，都要觉得这样是和这两个东西是一样的。Well， 这些元件怎么会认为它们是一样的呢？他们到了这边以后看到的电压是一样的，他们看到的流过去的电流也是一样，不就一样了吗？对不对？因为你能够看到什么，不就是电压和电流吗？所以呢，只要这些元件看过来的时候，电压是 V1， 是吧 ？V1， 然后流过去的电流也等于这个电流，他也搞不清楚那边是什么，他反正都一样。Okay? So basically, the current drawn by ZF from node 1, which is this current flowing here, must be equal to that drawn by Z1, which is here. Okay, so this current should be equal to this current. What is this current? This current is V1 minus V2 over ZF, right? What is this current? This current is V1 over Z1. So you can write on this equation. Okay, what about node 2? If you look at node 2, the current injected into node 2 should be the same as this one, right? Because this is injecting into node 2. Okay, this is injecting into node 2. So we can write on this equation, V1 minus V2 over ZF. It's minus V2 over Z1 because it needs to go into the direction to inject the current into node 2. Okay, so we can write down these two equations, and from equation number 1, Z1, we can rearrange this equation, Z1 to here, V1 minus V2 to the denominator right here. So it could be like this. Okay, so Z1, and if we divide it, if we divide both numerator and denominator with V1, then this will be 1 minus V2 over V1, which is voltage gain, right? V2 over V1, we say that this is voltage gain right here. The voltage gain from node 1 to node 2, we define as AV. So Z1 is equal to ZF over 1 minus AV, and Z2 is equal to ZF over 1 minus 1 over AV. OK， 所以呢，我们可以用 Miller Theorem。我们 apply 了 Miller Theorem 呢，我们就可以把一个 floating 的 impedance 变成两个接地的 impedance。然后这两个接地的 impedance 呢，是 Z1 跟 Z2。Z1 等于 floating 的 impedance 除上1减 AV。Z2 呢，等于 floating 的 impedance 除上1减 AV 分之1。什么是 AV 呢 ？AV 就是 V2 除上 V1。Okay, AV is the voltage gain from 1 to 2. Okay? So if you keep in mind for this Miller theorem, let's look at this fun part. So if we have a floating capacitance, and this floating capacitance is connected between input and output. Okay? So from V in to V out, and basically here we have a voltage gain as minus A0, and this is a floating capacitance. So what is Z1? Remember, Z1 is equal to ZF over 1 minus AV, right? What is AV? AV is minus A0. So 1 minus AV is equal to 1 plus A0. What is ZF? ZF is 1 over SCF, right? ZF is 1 over SC. Okay, so this SC should go into the denominator like this. Okay? And what is interesting is that this looks like a capacitance, right? This just looks like a capacitance with a very large capacitance, because the original capacitance CF now is multiplied by the term 1 plus A0， 对不对？所以呢，我们有这个 floating capacitance， 这个 floating capacitance 在前端这边经过这个 Miller theorem 之后，它就会等效为一个很大的 capacitance， 有没有很大？因为原本的 CF 要乘上一个 voltage gain， 它变成一个很大的 capacitance。This is what we call Miller multiplication. Okay? Miller multiplication means that if we have a floating capacitance, then it will generate an effective, huge, big capacitance at the input side, at the input node. 好，就是如果我们有个 floating capacitance， 它就会产生一个很大的 capacitance 在 input 端这样子。好，它是等效的，不是真的有那个 capacitance， 是因为它可以变成一个接地的大电容这样子。Okay? At another node, we can have Z2. Z2 is ZF over 1 minus 1 over AV. Okay? So this will be 1 plus 1 over A0 and times SC. And if A0 is very large, this could be approximate to 1. So this will be equal to SCF. So basically, at the output node, at the node number 2, we will have a capacitance which is almost the same as the original capacitance. Okay? So this means that we can convert the floating capacitance into two capacitance. We can, this figure and this figure, they are equivalent effectively. Okay, so one floating capacitance is equal to two grounded capacitance. One is very large, the other one is not very large. Okay, so let's quickly look at one example, 11.10. Okay, so now we have a floating capacitance between gate and gen. Okay, so gate is the input, gen is the output. This is a common source amplifier. What is the voltage gain? Voltage gain is minus GMRD, right? So voltage gain is minus GMRD. So this floating capacitance will be equal to two capacitance. One is 1 plus GMRD times CF. The other one at the output node will be 1 plus 1 over GMRD times CF. So this floating capacitance will be equal to two grounded capacitance, and basically this figure is equal to this one. Okay, the CF is equivalent as C in and C out. Okay, and C in is connected to ground, so there's a pole called C in 1 over C in RS. the other pole 1 over RDC out. Right? So we have one pole at omega in, and we have another pole at omega out. We'll have two poles. Right? Which pole is dominant? If we have two poles, which pole is dominant? What do we mean by dominant pole? Okay, this is the last thing I'm going to share with you today. Let's see. Not good. Erase this one. Okay. So if we have two poles, one pole is right here. This is omega P1. Another pole is omega P2. Right? So according to the Bode's plot, this will be 1. This is another one. Right? If we have DC gain is here. And when we get to here, we'll go like this. When we go to here, we'll go to like this. It will be something like this, right? So the slope here is minus 20 dB per decade. The slope here is minus 40 dB per decade. Right? We have two poles. Which pole is more important to decide your bandwidth? 我们有两个 pole， 哪一个 pole 对于决定 bandwidth 更重要？我们有两个 pole， 哪一个 pole 决定你的 bandwidth？ 当然是它嘛，对不对？ Omega P1 is going to decide your bandwidth because it is a lower frequency pole. So it decides when your frequency response will deviate from the DC gain. 好，所以 Omega P1 事实上是第一个会让你 voltage gain 掉下来的，会让你掉下来的那个 frequency 就是最重要的 frequency， 因为那个就决定你整个电路的 bandwidth 了，对吧？ So Omega P1 we call it dominant pole. Dominant pole. Okay? And keep in mind that all the pole have something to do with 1 over RC. Right? So to have a smaller number of frequency, you have a large capacitance or a large resistor. 对不对？我们 frequency 越低的 pole 越会影响你的 bandwidth。OK， 那 pole 怎么样 frequency 会低呢？因为 C 很大或者 R 很大，所以你如果有很大的电容或很大的电阻，它都会把你的 pole frequency 拉低，让你的 bandwidth 变小，对吧？ So if you look at this example, which pole will be the dominant pole? It will be the omega in. The reason is very simple. Because omega in, you are going to have a very large capacitance right here. Okay? Because you have a very large capacitance, so you have a very large C, and you have a smaller 1 over RC, which will be your dominant pole. OK， 好，今天好像差不多就这样就很 OK 了。好，那我们今天就先到这边吧。好，谢谢。